Hello everyone. I started record. I enabled the recording. You're attending the class of CS580. Today I will talk about the ray tracing. I'm Sung Yoon, the main instructor of this course, and I hope that can you hear me well? Also, can you follow also can you see the screen well? 잘 볼 수 있나요? 잘 들리나요? 오케이. 잘 된다고 하네요. Okay, thank you. So today, these are the today class objectives. Basically, I hope that at the end of the today lecture module, I hope that you can understand the basic ray tracing technique. Also, you can know each acceleration data structure and how to use that technique. Basically, I actually talked in the class. I will talk about the high level idea. But if you want to know the low level detail, I recommend you to go over my rendering book here by clicking the link. Let me click this link. So actually, I spent a lot of time to prepare this lecture material. So if you scroll down, you can see there is a part one. Actually, this is a rasterization technique. So in this class, we are not going to talk about rasterization, but in this class, we will mainly talk about the physically based rendering. So I guess chapter 10 is the ray tracing. If you click this one, you can see the detailed description of what I will talk about today here. So these are the lecture material. But before we talked about the lecture material, I'd like to briefly review what we talked about last time. Let me open up the lecture material that I talked about last time. I assume you already went over the older this material. So the last I talked about this one, but you should know that this actually obviously this version level, but we focus on the rendering, but also this is also the research oriented course. So you should know that. I talked about the different applications and other one. Basically the main goal is that we will study the basic concept of physically based rendering. And then to do that, also we'll study a recent technique and we'll discuss in project time. And then to know some of the recent techniques better, it is actually very important for you to implement the recent technique and then discuss of each project point. And as this project activity, you need to implement the recent technique, and so you will try to come up with a better idea that can improve this prior technique. That's the main activity of this course. You should know that. So these are actually some of the main topics. We will mainly talk about this Monte Carlo. We will mainly talk about Monte Carlo the rendering technique. So these are some of the main topics. And so obviously you need to have the basic programming skills, understanding on the data structure, also the basic. We assume you know the basic deep learning knowledge and programming. Unfortunately, we cannot actually talk about those basic skills. These are actually my book, actually textbook. This is free. You can freely access this link from this material from the web. This is very important. Basically, I will give you the lecture before the midterm exam. Then we will take the midterm exam. After that, you need to present. Each one of you need to present some of recent papers. So there half of the lecture given by me, and after midterm exam, you will talk about some of recent techniques. And also in your final exam, there will be the object form assignment. Also, I talked about you need to present some of the, I think the two recent papers, and then the main activity of this course is the team project. Some of you need to make a team and then implement some of prior techniques and come up with ideas that can improve the prior technique. That's the most important activity of this course. So and then so that's why in the end you need to do the paper presentation, also the final team project. You need to make a team of the 2 or 3 people. Maybe some of you wanted to have the solo project, but there are many students. So unfortunately, we can accommodate the solo project instead. If we have the solo project, there will be too many projects. We cannot cover all of them. So that's why we need to make a team. So that's why it's required for all of us to get together in the classroom, so we can get to know each other and then we make some interaction. And then first team, you need to pick your topic from the team, and each team member present the paper related to it. And then all team members work together, implement their prior techniques, and then improve those prior techniques. And then obviously you need to present what the team did for the team project. This is actually main activity: paper presentation and final team project. You need to aware of this course activity, and you need to prepare this activity. So that's why this class paper presentation takes 30% of the grading. Also, final team project then also takes 40%. So total 70%, right? For the class presentation, also this final project of the one. So that's the most important activity. Also, we assign the other 30% for the quiz and the coding assignment and some of the exams. I talked about the class attendance rule and some other one. And then this homework, right? Also, you need to watch the 2 SIGGRAPH Asia, also or the CPRP videos, some of top tier papers. Also, it can be the new whips and other one, ICML and other ones. And basically, you need to watch those. I do not recommend. I know that reading the papers takes a lot of time, but I do not ask you to read all the details of the paper. Just browse the paper, and then you need to know what are the topics in the field of this rendering in these conferences, right? And then write their summary. You should not copy the after of those papers there, right? Write down your own. Write down the summary of the paper, and summary paper the online. Different summary through online, different on the class. So before the next week Monday class, you need to prepare you need to watch the the top tier paper video and submit their summary. You can just one paragraph is enough, right? It doesn't need to be very long. So you can use English or Korean, whatever they are. And then if you go to the home page, let me open up home page. This is our first home page, right? First home page. And if you look at here, there are some of their online submissions here. Here, if you see that the paper video abstract, right? If you actually click this one, you can submit this paper information. But you should submit the recent paper. We will update this one. So you can go over the paper present in this year, 2021, 2020, 19, 18, and 18. So basically, you can actually present the paper that published since the 2018. I'll actually write down that information later on. Basically, I'd like to encourage you to look at the recent paper, not the old one, and then you can actually submit their abstracts through the here. Any question up to here so far? 뭐 지금까지 궁금한 거 있나요? 뭐 목소리를 하셔도 되고 채팅을 해주셔도 됩니다. You can write down your questions through the chatting. Also, you can write. Also, you can speak. 편하게 얘기해 주세요. 질문 하나 있나요? 주제는 당연히 이 수업과 관련돼 있어요. 렌더에 관련돼 있어야 되죠. 왜냐면 여러분들 여기서 수업이 프로젝트를 해야 되잖아요. 프로젝트를 해야 되는데 논문은 렌더링 아니고 다른 거 하고 이 렌더링 할 수가 없잖아요. 그러니까 이게 프로젝트를 해야 되니까 여러분 리슨 페이퍼를 알아야 되는 거고 그 프레젠트 하는 거고 그 프레젠트 하기 위해서는 뭐가 있는지 알아야 되니까 그 논문 찾아보는 것 다 속도되어 있는 거예요. 그런 거 좀 이해가 됐나요? 답변이 됐나요? So basically, you need to find the paper that are related to the discourse theme, the rendering, right? So that then you know what are the available papers. Then you can get to know some of the recent technique from those papers. Then you can find the topic for your team project. Then you can conduct your research for this team project. That's why this paper presentation homework and paper presentation in the class or the team projects actually align that way. But so to help you to conduct this final project presentation well, I designed the structure, I designed the Discord in that way. 아카이브 얘기하는 아카이브 논문도 할 수 있는데 아카이브 논문은 사이테이션 이미 있어야 될 거예요. 아카이브 논문이 좋은 것도 있고 아닌 것도 있거든요. 그걸 구별할 수 있는 거는 아카이브 논문 같은 거는 사이테이션 이미 있으면 좋을 것 같아요. So basically you can 그리고 그 논문 수업 시간에 프레젠트하는 건 아카이브 논문 하기 위해서 나한테 미리 허락을 맡아야 될 것 같고 이 페이퍼 서버리 하는 거는 일단 할 수 있을 것 같아요. 뭐 너무 많이 하는 것도 문제가 될 것 같은데 아카이브 논문 좋은 것도 있고 안 좋은 것도 있고 막 섞여 있잖아요. 그죠? 그래서 좀 그런 건 여러분 갈라서 하시면 좋을 것 같아요. So basically, you can present. You can actually go over some of their archive paper with some citation. You can do that. You can submit their summary. But when you want to present that paper at the class, you need to get permission from me early on. So we will have that kind of interaction later on. Okay. Do you have any questions? Okay, then I will move on. 왔네. 왔어요? 근데 마스크 벗어야 되는데 수업 하고 있는 거예요? 하고 있는 거예요? 내가 오늘 마스크 못 하려고 그랬는데 힘들어가지고. 위험하잖아요. 네. 오늘 하고 있는 게 있어요. 미안해요. 죄송합니다. 다시 한번 내가 왜 마스크 쓰고 내가 좀 눈에 병이 생겨갖고 한번 얘기해 주세요. 네? 여기까지 있죠? 오케이. So far we talked about their main class activity, also grading policy. Any question about that? Everyone clear on that? Clear on the grading policy, also their main class activity. 이 수업을 해야 될 때 여러분 해야 될 일이 어떤 건지 명확하죠? 오케이?
교수님,
네, 말씀하세요.
네, 혹시 다른 분도 똑같이 질문 아까 하셨는데,
네.
저 과제 이제 매주 월요일까지 매주 그냥 정기적으로 있는 과제라고 생각하면 되는 거죠?
매주 내시면 됩니다. 네, 2개씩, 너무 2개씩 벌써 매주 월요일 전에 수업 전에 내시면 됩니다.
네, 알겠습니다. 감사합니다.
Every month, right before every Monday class, you need to submit the two summary of some of recent papers. Okay, so these are the basic honor code and etiquette. So I strongly recommend you to recommend the collaboration among the team members. But when we have the problem assignment, obviously you can discuss about them, but everything should be done by yourself, right? Also, when you do the when you do the implement something for your team project, you can cite some other, you can actually you can utilize some of the code from the web for you to cite. Otherwise, you will get these are the basic class etiquette. When you sooner or later we will get to class. Okay, let me talk about the lecture material. Probably you heard about most of you may play the game, right? The recent games mainly use the random pipeline technique. So if you heard, maybe you heard about OpenGL, DirectX, right? Those kinds of techniques mainly implement this random pipeline. Mainly they call the rasterization process. But in this class, we'll talk about the ray tracing, which is not the classical random pipeline. In the classical random pipeline, maybe this kind of classical random pipeline, mainly known as rasterization, mainly covered in the undergraduate computer graphics course. So its main idea is that you set up the camera, also you set up your model and the scene in the 3D space. Then somehow it transformed your object in a way that it can project to film of the camera, right? So basically, here, let's look at this one. This action camera origin and camera looks in that direction to the distributed scene. So that actually distributed object, and then after the image space, image of the camera, we can call this film in here. But basically, this is nothing but some of the image plane, 2D image plane in here. And then rasterization, in a way, intuitively speaking, they project the distributed scene into the image space of this camera. That's the main idea. Then basically, here this image space of the camera, nothing but this kind of image buffer, 2D image buffer. Here I'm only showing the descent of each pixel. This is actually the 2D array of the image, and I'm showing the descent of each pixel. And then once we projected every typically we use triangle to represent this 3D scene. Once we projected this triangle into the image space, basically they are mapping to this kind of space in this image space of the camera. And our goal is that in the rasterization process, the class random pipeline, nothing but basically when the center of this pixel are within this triangle with the color. In this case, this kind of sky blue color. That's the main idea of the rasterization. There are lots of the steps. To do that, actually, we do the modeling phase, modeling transformation, some of the trigger rejection, illumination, viewing transformation, clipping, projection, rasterization, and also then we display the images to the monitor. These are actually some of very well-known concepts in the classical random pipeline. But I'm not going to talk about the detail of this one. But basically, if you know this concept is useful. But we will basically also in this class is undergraduate course, and then and we assume that you know some of the main concepts like what's the camera, and then how do we represent 3D model in the scene, how we can set up how we can compute the color, and so on. And then basically there also I prepared a short summary of the undergraduate computer graphics over there. If you go to our course homepage again. Yeah, here the summary of undergraduate computer graphics. So if you're interested, you can go over this one. But they are mainly coming from the undergraduate computer graphics course. Actually, we are using this rasterization a lot, mainly because it's so fast. Also, they provide a reasonable high quality. And then you might heard about the GP architecture. I think that I actually prepared this slide maybe 5 or 6 years ago. Around that time, there's the Reformi GP architecture. I'm not going to talk about the details about this architecture, but it's mainly you can see that this green box is nothing but a CUDA core. You can treat that this is a very simple CPU core. It's not exactly CPU core, but you can see that it's very compact CPU core. You can we typically call that the GPU core or the CUDA core. When we talk about the recipe process here, basically there are so many pixels, right? But here actually we need to determine that whether this the center of each pixel are within this triangle or not, right? But basically we can process we can perform that process independently across all the pixels, right? So in other words, we can use a lot of the many cores, right? So we can allow the region for the rasterization process. That's why GPU early on evolved in a way to have the many parallel cores like this. And this is a theory architecture proposed in the 2018. And actually, the GPU core evolved more. In a way, it actually had this shader and compute core. Basically, the shading is nothing but computing the color. So they call the shader. It is nothing but some of the compute operations. So actually, it has name of shade and compute. I'm sure the GPU chip. Also, the recent actually ray tracing become the more more important application. That's why actually recently GPU also dedicated chip area for the ray tracing core. So you actually it design chip structure to support the ray tracing core. Also, you know that actually maybe 10 years ago, GPU actually used for even their deep learning AI technique, right? Also, the GPU technique evolved in 2018 by using the theory architecture. They also dedicated certain chip area and the tensor core, this area, to support some of tensor operation commonly used in the deep learning. And back then, they only had this shading compute. They only had mainly this shading and some of their this chip mainly designed for the graphics application. But 2018, now actually they can support the ray tracing of deep learning. And this is their this Ampere architecture developed in 2020. Basically, it's more core, fast computation than from this tuning architecture, but essentially they are similar structure. So that's why actually GPU actually provide a lot of core, so that we can actually accelerate. We can run the rasterization very fast. Also, that we can actually have this kind of very nice image long time ago, right? But what about other cues? When you look at this scene, there are many cues. You can see that there are very soft shadow, and also there you can see that you can see that this light energy. You can see the light source reflected onto this sphere, and the shade. Also there you can see that there actually this wall actually has a green color. So you can see that this green color also reflects somehow you can see that this green color on this part of the sphere, right? This is known as the color bleeding. Sometimes they use they feel that the color is bleeding, each color is there, so they use some color bleeding. There are many this kind of this kind of visual effect. But actually, the rasterization developed a lot. Rasterization technique developed more than 30 years ago. And actually, they can provide this kind of the effect, but you require a lot of engineering. Actually, I'm not talking about all the lower details. You require a lot of engineering to use the rasterization to perform this kind of to produce this kind of effect. But on the other hand, if you are using the ray tracing, you can actually very easily support this kind of effect. So the ray casting, or some people call recursive ray casting, actually they're introduced to the computer graphics 1980 by the Turner Whitty. He's active in the Microsoft. And then back then, it's a very long time ago, more than 40 years ago. And then back then, by using the ray tracing, now the only version of ray tracing, you can support this kind of shadow and this kind of transparent sphere. You can see this shadow and other one. So back then, actually, they felt that by using their recursive ray casting or ray tracing could be used for global illumination that we'll talk about today. I will talk about the ray casting and ray tracing. So let me show. Let me explain this concept through this kind of illustration. So basically, there this actually this here actually we have the camera and this image plane that we want to compute color, and then this every single pixel, and then if you want to color from this pixel, you generate an array from your camera or origin that passing through the center of this pixel, and then keep going on. And typically this rate known as this primary rate, and then basically this actually if we do this one, this is called actually ray casting. We cast a ray from here to there. So ray that cast from the eye point here we have eye through each pixel in the image, right? This is ray casting, and then so to compute color, we compute the intersection point between this ray and the solar prime in the scene. In this case, assume that this cylinder, that we got the color from the at the intersection point from between this ray and the thin triangles. We get the color from here, and then we transfer the color, we show the color to there. That's the main idea of the this ray casting. How about supporting the shadow? Also, it's very easy for supporting shadow in the ray tracing. Is there anyone who knows how we can support the shadow in the rasterization? 자, 여러분, 그 rasterization 에서 섀도우를 어떻게 서포트하죠? 어떻게 하죠? 다이렉텍스는 오픈GS는 그 어떻게 해요? 그 섀도우를? 여기 아무도 없는 거예요? 나만 여기 얘기 수업하고 있는 거예요? 다른 친구들은 뭐 하고 있나? 효과가 있나 없나 볼까? 아무도 영상도 안 보여주고 나 혼자 얘기하면 되는 거 지금? 여러분 저 외로워요. 뭐 얘기 좀 해주세요. 모르겠습니다. We have no idea. 솔직하네. 좋아요. That's very good answer. If you don't know, just say no. Yes. In the rasterization, actually, we can use the shadow mapping technique. I don't know whether you, actually shadow map, understanding shadow mapping technique is very difficult, even in the undergraduate, even though you took this undergraduate computer graphics. Should the ray from the light source first and get use each map? Yeah, that's actually shadow mapping technique in a way. Thank you. 섀도우 매핑 테크닉 되게 어려워요. 여러분 학부 때 그래픽 수업을 들어도 섀도우 매핑 테크닉 이해하기 되게 어려워요. 하여튼 괜찮아요. Basically, shadow mapping technique is very difficult in the rasterization technique, but in the ray tracing technique, it's very easy. So for the same thing, we actually generate primary ray from the camera origin to passing through the center of each pixel, and then we do we find the intersection point between the ray and the scene. Here actually we have the hit here, right? And then if you want to know that actually, in this case, you are in the you want to know whether in this region are within the shadow region or not, right? To know that, we can very intuitively generate, we can generate another ray from here, from the intersection point, and to the light source. Then if you can reach from here to there without having any collision, without having any section against the scene, it means that you can see the light source from here to there, right? Then you can get the energy from the light source, right? But in this case, if you generate the shadow ray, we call this actually a shadow ray, and then if you generate shadow ray from here to the light source, and then there will be the intersection between this shadow ray and the scene. It means that you cannot see the light source from there. Then you cannot get the energy, right? And then you probably, since you cannot get the energy, it looks very dark, right? That's how we can support the shadow ray in the ray tracing. It's very simple, right? And then so actually this is known as this primary ray. And then here we recursively generate another ray. to support this kind of shadow, right? And this called known as is the shadow ray, also the known as is secondary ray. 두 번째 ray가 있죠, 둘째로. Primary ray and also this secondary ray. And then, as you can see, we recursively perform this ray casting. So we recursively perform this ray casting, and that algorithm known as the ray tracing. That's the ray tracing. If you want to do the here, actually, this is this time this cylinder actually made by matter, so it looks like it looks like mirror, and then so that actually it can reflect you can see the surrounding scene on the surface of this mirror, right? And then how we can support this reflection. The ray tracing is very easy. We generate primary ray again here, and then if this this model is mirror-like matter, then we actually generate a reflecting ray from here to there, and then this ray the hitting here, and then we actually transfer that color of the floor from here to there and there, so that we can get this kind of the image actually. So it's very easy to support this kind of effect in the ray tracing. That's the main basically this simplicity is the main benefit of the ray tracing. Refraction, 굴절되는 거 말하는 거죠. So in this case, this looks like some sort of glass, but it actually refract the energy. Then we generate primary ray. It is actually looks like glass, and then we refracted energy from here to there, and then we refract this ray and generate another refraction ray, and then we keep doing that, and then if it's hitting to there, we transfer the color from here to there, and then up to there, so that we can get this kind of image. So how can we generate this kind of refraction ray? I'm not going to talk about the kind of low level detail, but actually we can use this Snell's law that we learned from the physics course, right? So that's why actually for ray tracing we can actually design this kind of the rendering image. We can compute this kind of the image based on some of the physics. I'm not going to talk about the low level details, but if you're interested, I recommend you to look at my book. So it talks about all the low level details. Basically, let me briefly talk about some of illumination model. So this is actually foam illumination model. Some of you, if you took the undergraduate course, you might heard about this illumination model. But the 1980 long time ago, Economic designed this kind of model. I'm not going to talk about the low level details, but here main idea is that somehow when you generate ray, it carries some energy, light source energy, then you're adding something like that. But I'd like to talk about some of the basic terms here, ambient, diffuse, and some other one. This is actually you might heard about OpenGL, right? OpenGL is kind of API to do to make their graphics applications. It actually has your ambient, diffuse, specular term. I'm not going to talk about the low level details. This actually this already covered in the undergraduate course. Again, if you want to know the details, I recommend you to look at my book. But the ambient is kind of the ambient, diffuse that looks like this, and specular looks like this. Specular is basically it's the highlight. It's the kind of view dependent one. If you're adding this ambient, it's kind of background color, and diffuse is the 이거 우리나라 말로 이거 난반사. So when you look at this kind of blackboard, basically I can look at this blackboard from here, right? Also I can look at the blackboard from here to that direction. How is it possible? Since this blackboard diffuse material, it means that once you receive the photon from the light source here, then the surface of this blackboard is rough, and then so that actually it reflected at the photon in arbitrary direction in the same amount of energy. That's the one of the underlying physical explanation. Anyway, that's a diffuse term, and specular is basically when the surface is kind of metal-like or the mirror-like, it actually reflecting energy in such an area. But anyway, OpenGL has this ambient, diffuse, specular, and then by adding this one, we can actually have this kind of very nice image, long time ago actually. And as you can see, it looks like the plastic, right? So that's why actually it's one of the reasons why the Toy Story becomes the Toy Story. You might heard about Toy Story Pixar, right? This is one of the reasons why the plastic toy, the Pixar made the movie out of this plastic toy. But anyway, basically based on this one, we can compute color, and then by utilizing this kind of concept, we can also apply the ray tracing, and somehow we can compute color. I did not talk about low level details, mainly because it's not really important for our discussion here. But as you can see so far, I didn't really talk about the physically based approach, right? But actually, I will talk about the physically based rendering step by step later on. But anyway, the main concept of the ray tracing is that if you want to suffer some effect, you generate ray. That's it. That's the main concept. But the problem is that to support that effect, we need to generate so many rays. Suppose that given this, we generate primary ray, we hit it there, and then this material may be reflecting a mirror light, so that we need to generate reflection ray from here to there, and also it also has this glass light effect of material type. So also we need to generate a refraction ray, and then also we need to know whether we can get the energy light source from this light source. So we need to generate the shadow ray and so on. Also, we keep doing that process from here, every single point, right? So that we need to generate so many rays again and again, and in a recursive way. So if we be visualizing this ray structure, the generation process of ray into like this kind of tree structure, given this given this primary ray or I ray, if the material is there, we can generate a reflection ray, also shadow ray, also the refraction ray. Sometimes we call it transmission. 추가 된다 그러잖아요. 추가 그렇죠? So actually we have the key here. For every this one, we can generate another reflection, shadow, transmission, and so on. So the ray tracing, it's a very nice idea, but it generates so many rays, it takes too much time. So early on, people know that ray tracing can be used for generating very nice imaging, but this missed long time ago since it's so slow. We didn't have the architecture GPU and CPU to support this kind of to handle this kind of so many rays. Any questions so far? 지금까지 질문 있나요? 질문 있으면 편하게 하세요. So the main point that I like to give is that we can use the ray tracing for generating high quality images, but there are so many rays. Okay. So think about it. We need to generate this kind of image, right? We need to this kind of process for every single pixel, right? So that early on, there actually has been acceleration technique for ray tracing. Rendering time for ray tracer depends on the number of ray intersection paths for each pixel. Basically, for each pixel, I mean, if you want to generate this kind of image, basically, as we get more pixels, it takes more time, right? So the rendering time of ray tracer governed by the factor of the number of pixels multiplied by the number of primitive in the scene. Why? For each ray, we need to go through every single triangle, and we need to see that whether that triangle actually has an intersection against with this ray, right? So that if there are more triangles, so that I use the term of this primitive. Primitive is actually you can treat that primitive nothing but triangle. If there are more triangles, we need to do the more intersection test between ray and these triangles. It takes more time. we need to reduce down the number of pixels, number of primitive, so that we can improve the render time. So early on, a lot of the research efforts focus on the accelerating ray and object, ray and triangle intersection test. Maybe 4 years ago, maybe 4 years ago, we did a lot of paper on that, but still slow. So that and then maybe also there long time ago also the more advanced technique required to make the vector practical, so that bounding volume hierarchy and some other technique actually developed. So typically I'd like brief touch on the concept of bounding volume. Which means bounding volume nothing but bounding volume is nothing but simple object like this kind of sphere enclosed complex object with a simple to intersect object. I'm not going to talk about details here, but it's very easy to perform the intersection test between a ray, which is nothing but line, and the sphere, right? You can do some sort of mathematical. We can derive some of the mathematical equation to perform the intersection test between the ray, line, and the sphere. So that actually we can use this kind of sphere as a bounding volume. So in this case, if this ray actually if we generate ray from here to there, then first we need to check whether there's intersection between the ray and the sphere. That if there's no intersection, it means that we don't need to go through every single triangle within the sphere to check the intersection point between the ray and triangle, right? So that actually we can skip that complication. It accelerates a lot of speed up, right? But if there are intersection between this ray and this sphere, including this underlying geometry, then okay, we waste our time. We need to go over every single triangle within that of that object, and we check the intersection test between ray and every triangle within the sphere, right? So that early on, there actually has been many papers to design this kind of bounding volume sphere, spherical bounding volume, axis aligned bounding box, which is like box in 3 space. Another sphere is a very easy to compute chip test, but it can be very loose fit, right? Basically, the bounding volume should be very tightly enclosing the object, right? For example, here this actually orient bounding box, it can very tightly fit the object, right? But it's a little bit basically constructing this bounding will take some time. Also, they're checking the intersection test between ray and this kind of orient bounding box more expensive compared to this sphere. There are all kinds of pros and cons. We cannot say we cannot say that which one is best. So there are actually so many techniques: sphere, axis aligned bounding box like this. Also, the orient bounding box, or some other flat or K dots that using the K different plane to fit this kind of object. We cannot say that which one is the best, but there's been a lot of the techniques. But commonly, the sphere and bounding box, this axis aligned bounding box is commonly used since it's very easy to use. But this concept hierarchical approach is common hierarchical approach is used a lot. So basically, its main idea is that the computer scientists like the hierarchical approach, right? So we organize bounding volumes as a tree. Here, given these scenes, we compute the big bounding box like this, that covering that enclosing every single triangle. Then we partition this object into this different one. In this case, 4 different parts. This part and that part, this one here, right? And then for this one, we can also partition the underlying object and so on. And then based on this hierarchical partitioning process, we can compute this kind of the bounding volume hierarchy. For the big one, this is actually root node, having the biggest bounding box. Suppose we actually gonna partition the scene in that way. Then for this one, we got a small bounding box here, another one, which is actually children node like this, and then we keep doing that, right? So we can do this kind of bounding volume hierarchy. Then how can we use this one? Given this array, given this array at one time, we first check there's an intersection we check whether there are intersection between this ray and root node. In this case, there is intersection here, right? Okay, then we need to traverse differ, right? Then we need to check the intersection between this ray and every single child node. For this one, okay, intersection. And then we since there is intersection, we also we need to differ here. This one, that one. We check the intersection between this ray and here. Okay, yes, we keep doing that. And then we differ. Over there we have triangle. And then so that we do the we go through every single triangle and we do the ray and triangle intersection test. Nothing there, right? You can see that somehow that passes through. There's no intersection here, right? And then we keep to we repeat this process. For this one, there's no intersection. There's no intersection between ray and box. Then we skip this part, traversing this region, right? So that we can accelerate this. We can accelerate this rendering process. This approach. That's the main idea of using the bounding volume hierarchy. Any question about this one, bounding volume hierarchy? Very easy concept, right? Well, actually, the 2006 is it may be very long time ago for you. Maybe it's a very long time ago, 16 or 17 years ago. I was young at the time. I was at the time actually I was I graduated there, but actually I got a very young a junior student at the school. So actually I was kind of this supervised student to him, and then we actually in this paper actually we proposed to use the bounding volume hierarchy, this concept using bounding volume hierarchy to the ray tracing. Back then I thought that it's a very simple idea, it cannot be a paper, but 10 years later, 2015, this paper actually received the Test of Time Award, 2006 award. It means that they look at the 10 years old paper, and then they find the paper that gives a lot of the citation of impact to the field of computer graphics. And our paper chosen as this one of the paper that gave us a lot of impact in the field. But anyway, at the time I didn't know that this is actually this idea will have the kind of impact. But anyway, it's a very simple idea using the bounding volume hierarchy for the rate. But there are many other structures. But I'd like to point out that maybe 15 years ago, this kind of using bounding volume hierarchy was the main. Actually, I mentioned that it's very simple idea, but there are very fierce competition between our group, also and many other groups to accelerate this ray tracing. Somehow, actually, we made this paper back then. So maybe 15 years ago, actually, they're using this kind of hierarchy to accelerate ray tracing. Actually, researched a lot. But still, the performance of ray tracing has been improved, but still, actually, it has many problems. Still, actually, it can provide some interesting effect, like the shadow, also this kind of transparent effect. But it's not realistic at all, right? So we definitely need we definitely need better technology and fast. Also, this technique that can generate very realistic effect. Also, in the case of rasterization, we can use the GPU. So there are many parallelism, but back then, the ray tracing is very hard to accelerate with the special purpose hardware. In other words, GPU. I mean, they had a lot of the effort to develop some dedicated hardware like GPU for ray tracing, but there had been many efforts, but they were not successful. But I mentioned that before. Around 2018, just how many years ago? Just 4 years ago, NVIDIA chip dedicated each area to support this ray tracing with the GPU. So it means that now we can use GPU techniques we can use the GPU to accelerate ray tracing. So there has been lots of the evolutions in the field of ray tracing. I cannot talk about lots of things, but I can mention that I can point out that ray tracing now actually can support from the GPU. Now we can have the reasonably fast GPU. So let me talk about some history. It can be deeper. Classical ray tracing. So far I talked about classical ray tracing. It's not realistic. Also, it's field dependent. It means that to generate image, I set up the camera, I generate so many rays, and then it spend 1 hour, 2 hours, and I got the one image. And the next time I generate, I actually move my camera from here to there. Then I need to do that process again. It's a field dependent. It means it takes a lot of time. And later on, the 1984, still a long time ago, Rasterization actually proposed. It's a very groundbreaking technique, global illumination technique in diffuse scene. It's not field dependent. I'll talk about the Rasterization. And 2 years later, 1986, actually this is groundbreaking technique, Monte Carlo ray tracing. This this global illumination technique for any kind of environment. It's more than I don't know. It's very old technology. But just recently, this technique, maybe 7 years ago, now they'll be actually using this technique, Monte Carlo ray tracing technique, to even generate a movie. The recent Pixar movie actually based on this Monte Carlo ray tracing. That's why actually I spend. That's why we will actually we will have in this course we will study this Monte Carlo ray tracing. Main because it's now mainly used in many movies and even games, and then the future is on this technique. That's why we'll talk about this one. So I talked about the many different techniques: ambient, diffuse, wave, triangle detection test, bounding volume hierarchy. But that's the past. Already, you know, NVIDIA was Intel. They prepared the ray tracing engine kernel. In the case of the rasterization, get OpenGL and DirectX. Actually, this kind of company wanted to have the very kind of the OpenGL and DirectX kind of API for ray tracing. That's why NVIDIA prepared the OpticsX. Actually, NVIDIA OpticsX implement everything that I talked about so far. They actually they can utilize GPU. We can use the GPU computer architecture in CUDA to perform the ray tracing a lot. And then Intel also have this Embryo architecture. The Embryo actually utilize CPU, multi-threaded and SIMD structure, SIMD instruction to actual ray tracing. So now I will talk about our first problem assignment. Some of you already started with the PA1. So back then, actually, long time, maybe 5 years ago or 10 years ago, I give this first problem assignment that implement the basic ray tracing. Now we don't need to. It's already implemented in the OpticsX memory. So just download it, compile either one of those two methods, and just you can also just using this pre-compiled ones, try it out a few scenes, and then you can generate this kind of image and upload this final image to the KLMS. And then the deadline is already given. You can check the KLMS, and then obviously this is very easy one, but they're actually compiling and linking this kind of one. They're always surprised. So it may take a lot of time. So I recommend you to start early. So for the details about problem assignment, the spec of PA was already given in the KLMS. And then if you have any question about them, I recommend you to ask to the TA. Any questions so far? 지금까지 질문 있나요? 이해 안 되는 중 있으면 얘기해 주시면 감사하겠습니다. 빨리 끝나오신가요? Okay, this is PA1. Another homework. I mentioned this one. Go over the next lecture slide. I will prepare. I will provide the next lecture slide sooner or later. Go over the next lecture slide before the class. That way you will be ready to take the next material and watch watch 2 paper and video and submit their summary right before every Monday class. Just I mentioned just one paragraph is enough, right? So by going over this video and paper, you can know what are the recent topics in the field. That way you can actually come up with the team project idea topic for your team project. That's why actually I had this homework. This you do that this homework. You need to do this homework every right before every Monday class. Okay, so far I wish that by now you can understand the main concept of the page ray tracing, know its acceleration data structure and how to use it. And next time I'll talk about velocity. That's it. Do we have any questions? 질문 있나요? 숙제에 대해서는 저기 KF에서 보시고 조교랑 얘기하시면 될 것 같습니다. Question: Is it sufficient to check one in the center which pixel when ray tracing? Obviously not. 이렇게 내가 설명 여기서는 지금 먼저 되게 좋은 질문이 잘 파악을 했고요. In the end, 픽셀에 한 레이를 하나만 쏘면은 하나만 쐈는데 유닛 퀄리티 안 좋아서 보통 영화에서 찍고 있을 때는 몇백 개 쌓여요. 몇백 개 쌓아야 돼. So typical we need to generate the very high quality image. We need to generate hundreds of rays even for each pixel. Does it answer to your question? 근데 한번 물리적으로 생각해봐요. 물리적으로 이게 실제로는 think about it. Think about everything in a physical sense. Ray is nothing but photon. Through the each pixel, how many photons we can receive, right? So to generate this kind of real image, how many photons we are receiving through one pixel area? Then generate hundreds of rays not enough. Okay, I will conclude that. I will conclude this class with that question. Thank you so much. Bye. 다음에 봅시다. 오랜만에 이렇게 강연 힘드네. Bye. 됐나 모르겠다. 이게 녹화 이렇게 된 거 아니야 이거?